Hello everyone, and let's start this new chapter which is known as electromagnetic induction. In short, we call it as EMI, that's electromagnetic induction. And this is very important as well as interesting chapter. In this chapter, the learning objective will be this. We will start from this magnetic field. Till now we have understood what the magnetic field is, how to calculate the magnetic field because of various current distribution. So because of current, there is going to be magnetic field coming in. And if this magnetic field changes, so if varies over the time, let's say, so if it is time variable, then you'll find this magnetic field going to create electric field. And that's a very interesting point, that a changing magnetic field is creating electric field. And this electric field is not because of charge, but because of varying magnetic field. Hence, it will be known as induced electric field. And whenever this electric field is there, and there's a conductor placed, so in that conductor there are charge, and this electric field is going to move those charge. That means this electric field is going to create a current, and this current will be known as induced current. And then this mechanism is called induction. So that's called induced or induction, we can say, or induced magnetic field. And then this is induced electric field, this is induced current. So that's induced current. So this is the whole objective for this particular chapter. So from current, we need to know what the magnetic field is. If it varies over the time, so it creates electric field. There comes induced current. So we will start to learn this process in this particular lecture. So let's start with this, how we reach to this induced current and induced electric field because of magnetic field. So the first quantity that we need to understand is magnetic flux. So magnetic flux we denote by phi. And how we defined it as, it is the number of magnetic field lines passing through a given surface. So we can write in short, it's a number of magnetic field lines. Definition is very similar to that of the electric flux. Magnetic field lines passing through any given surface. Passing through a given surface. So you choose a given surface and see how many field lines are crossing. That number is proportional to magnetic flux. And let's say magnetic field is acting like this, as shown in this picture, and this is the surface we are considering. So we need to find how many field lines are going through the surface. For that sake, we need to know what the surface area is. So this area is denoted by A vector, and you know this A vector is going to have a direction perpendicular to this surface. So it's going to be perpendicular to this surface. So this is the direction of A. And cap is basically the direction of A vector, and B direction will be given to us. So we can see what the angle these two vectors are making with each other. So mathematically we can write this magnetic flux as phi is equal to integration B dot dA. If you remember this flux definition in electrostatic, exactly same, we had phi is equal to B dot dA or ds. Here dA we are using for differential area element, B is the magnetic field. So this is the magnetic flux because of magnetic field through a surface, right? And here the terms, what the terms are, let me say about that. dA is differential area vector perpendicular to the surface, so that is differential area vector. And you have understood this area can be made a vector by giving the direction perpendicular to the surface. So direction is perpendicular to the surface. And what this B is magnetic field, or net magnetic field for that matter, magnetic field, where this is at the location where you are opting this dA. So this is magnetic field at dA vector location. So its location is dA vector. And if it is uniform, so that will be same at all the points, then we can simplify this integration. right? So let me give that aspect as well, because mostly we are going to use this. So if B is uniform, when we say uniform, that means it is same at all the locations. So if B is uniform, now here one point need to be differentiated. Uniform means with respect to position, that means at all the location it should be the same. However, B can be time variable. Time variable, if it is that can also be uniform. So that means if it is same at all the location, then we call it as a uniform. And if it is a variable with respect to time, so we can say variable. If it is not with respect to time varying, then we call it as a constant. So there's a difference between the term called constant and uniform. So uniform is with respect to the position. So if B is uniform, then how much flux will pass through? So you will write the flux will be equal to phi will be equal to, B is uniform, and we are trying to find it with some area. Let's say this area, and area is lit open plane surface as the picture shown there. So let me make this picture a bit downside. So we are talking about this picture now, and B is uniform. So we will say it's going to be integration B dA cos theta. Theta remains constant, B is a constant, uniform, so we can take this B outside, cos theta outside, and it becomes integration dA. And if we integrate this entire part, so we will get this entire area coming in. So you'll find the flux will become equal to B into cos theta. That will be our formula for calculation of flux in the case when magnetic field is uniform. Moreover, sometime it will say that there are n number of turns. So if there is n number of turns, so we can apply n over here, because in each and every loop, so one loop will have this flux. So there are n loops or n turns, then you will get n as a factor, right? So n is going to be applied when there is a number of turns more than one. So this is the flux from this loop if this has a single turn. If there are multiple turns, then we can say. And you can say loop or you can say area. When we say loop word, that means we are basically considering this entire area. And if we are saying area, that's also having the same meaning. Anyway, so from this area, this is the amount of the flux when this is a constant. What is a constant? When this is B is a uniform. Uniform means it's with respect to position. Now one more point we can add here. Simple point. Sometimes you will find that B is not uniform. So if it is non-uniform, so we need to follow this formula per se. So that's what I'm writing over here. If B is non-uniform, so in that case, we need to say the flux will be given by the original formula itself. So we cannot use this formula for that. It's going to be integration B dot dA, and if it is non-uniform, that means it will be given to you, and you can go for this integration, simplify the way we had done in case of electrostatic. So you'll get the flux from there. Makes sense? So that's the basic definition of flux, and it's two cases, uniform and non-uniform. Okay, so next point that we are considering over here is Gauss law, and this Gauss law is related to magnetism. Earlier we have talked about the Gauss law related to electrostatic. Similar concepts are there. So it says, what it says, let me write this statement: net magnetic flux, net magnetic flux passing through any closed surface. For Gauss law, we choose a closed surface called Gaussian surface. So net magnetic flux passing through any closed surface is always zero. So that's a law for magnetism, Gauss law for magnetism. How the statement mathematically will be written as, if we are calculating the net flux from any closed surface. So we place this loop, if you remember, for closed surface in integration, so that becomes definite integration, and this will be B dot dA. So that will be known as net magnetic flux. So either you write by phi or you write by this expression, and this value will become 0 for any closed integration. That means if there is this loop, then answer is 0. That's the point, because loop means closed, and this answer will become 0. So whenever there is a loop in integration is there, and it is related to this magnetic flux, you answer it as a 0. And that's important aspect, right? So that's important formula. That's why I'm placing it in a box. So this is called Gauss law of magnetism. And why this is happening? So we can see that let's say we are having this closed surface or Gaussian surface. So if there's a closed surface and we need to find how many field lines effectively passes through this, we know ingoing flux and outgoing flux and all that. Magnetic field lines, they are always in the closed loop form. So if we draw the magnetic field, there can be three types of cases. One case will be that a magnetic field lies entirely inside the closed surface. Another can be that it intersects like this, depending upon how the current distributions are. And another case would be like this. Now, this is our closed surface. We need to find the flux out because of this, and these are the magnetic field. These are the types of magnetic field that I'm drawing. Either they will completely lie inside, or they will intersect it, or they will be completely outside. When we calculate the flux surface, right? So this, let's say we call it as a first case, first type of. This is the second type of field lines. This is third type of field lines. So can you think of what the flux will be coming because of this first type of field lines? So this first type of field lines are not intersecting the surface. If the field line is not intersecting the surface, its contribution to the flux will be 0. That will have a 0 flux contribution. These kind of lines will be affecting, that is coming inside or going inside, then coming outside as well. So if the field line is going inside, it must come outside. Why? Because it has to make a complete loop. So that means in this case there will be non-zero flux which is going inside and non-zero flux going inside, but we say outside, but we say this ingoing flux is a negative, outgoing flux is a positive, and they are equal in number. So that will ultimately lead to that second flux will also be 0, or flux due to the second type of lines will also be 0. Third, if we talk about this third case, then you'll find this third case is not intersecting the closed surface. So flux because of this third type is 0. So that means all type of fields for this particular closed surface will lead, the field lines will lead to 0 flux. Hence, the flux will always be 0, no matter how the field lines are, as long as your surface is a closed surface. And this is solely because of the property of magnetic field lines as magnetic field lines. So that property is important. Magnetic field lines form closed curve. So whenever any field lines will form closed curve, you'll find their flux will always be 0. Electrostatic, we got the Gauss law as Q upon epsilon naught, because that side was non-zero, simply because electric field lines are not in the closed curve form. They are in the open curve form. They emerge and they terminate. However, magnetic field line neither emerge nor terminate. They are in the closed curve form. So this is information that one has to remember. A simple practice example is here. So let me read this example. It says the number of turns in a long solenoid is given. So number of turns are given to us, and it says the cross section of the solenoid is also known to us. Induction, that's a B. Passing through when this 2 ampere current is being passed through is given as, so B is also given to us. Magnitude of magnetic flux we need to find in Webers. Weber is the SI unit of phi flux. So we need to basically find this flux. So what do you need to find? You need to find flux, and we know in long solenoid it's uniform, and so we can write it is going to be N into B into A into cos theta. This is the formula you need to apply. So if you apply this formula, put n value is given to you, b value is given to you, a value is given to you, theta you need to identify. And if you remember in solenoid, the field lines are along this thing. So let me give you a hint. So this is a solenoid, and this kind of current carrying wires are wrapped. And then this magnetic field used to be along this, depending on the current, right? This will be when the current is like this. And if this is a magnetic field, if you look at the cross section, so cross section's perpendicular direction also is going to be in this direction. So you can say the angle between them is 0. If you can catch this angle, then you can find what the answer is going to be. So you need to solve it. And there are 4 options, A, B, C, D. Write the correct option in the comment section. So you need to give this answer in the comment section after solving this. And this is a very simple problem, straightforward problem in calculation of magnetic flux. So just solve it. So now we will be talking about this most important law of this electromagnetic induction, that's called Faraday's law. And that's very critical to this chapter, and it will link that thing, magnetic field, to the induced electric field. What the statement is, so let me write that in proper sense. So it says when magnetic flux, so I'm writing phi with B for magnetic flux, through a closed conducting loop changes. That is the condition. The condition is when magnetic flux through a closed conducting loop changes, then an induced EMF, electromotive force, you must be knowing that. So then an induced EMF is created in the loop. So what are the critical terms over here? Let's have a glance on that. There has to be magnetic flux, first of all, and this magnetic flux has to change. So this law will be giving the results when the flux is changing. So first of all, there has to be a magnetic flux. Second, it has to change. And from where it has to change? Through a closed conducting loop. So there has to be loop, not a surface. Look carefully. And through that loop has to be conducting in nature. And of course, that has to be closed. So these all terms are very important. If this happens, then an induced EMF, that means electromotive force, gets created. That gets created in that loop. So since that is conducting loop and EMF is being created in any loop, so expected is that is going to be current running it. Let's say it's like this. This is a loop, and in this loop you are creating a battery or EMF. So can we say, and this will have its own resistance, so we want to draw its a simplified circuit, it can be like this. So this is EMF that is being induced, and this is the resistance of that loop itself. So you'll find there's going to be current running it. So how much the current is going to be? Current is going to be EMF divided by resistance. So this is how we will reach towards this current. So what the Faraday says, this will be induced, or this will be created. You are not going to apply this. It's going to be created automatically if this is the condition through the conducting loop. And how much this EMF is, if we can get this thing, then of course we can get what the current is going to be. So that's a rough relation with the old concepts that you have learned. And moreover, this Faraday's law also gives us what that EMF is, or what that induced EMF is. So it says induced EMF, next point you can call that induced EMF that will be created is given by EMF, we write by this E. So this E is going to be equal to minus d phi by dt, d phi due to magnetic field by dt. So this becomes the formula for induced EMF through the loop. So this is formula given by the Faraday. And what this phi b is, phi is a flux, and it is due to magnetic field. So that's why I'm writing b, or you can simply write it as a phi. So this phi b is indicating magnetic flux. Magnetic flux. Which flux? Magnetic flux. And that is passing through that closed loop. So flux passing through that closed loop. Magnetic flux through closed conducting loop. Closed conducting loop. And just prior to this, we have talked about how to calculate this flux. So basically this flux has to be calculated by using this formula. This is going to be integration b dot dA. Now we are calculating it through a closed loop. So should we place a circle over here or not? We are calculating it through a closed loop. Should we place a circle over here or not? So your answer should be that we should not place any circle, because if you are placing the circle, that means you are doing in a closed surface. And in that, if we place the circle, so it becomes a closed surface, and that's as per the Gauss law is always 0. So this closed surface is not allowed over here, because this closed circle indicates closed surface, because integration is over the area. Here we are taking the name of closed loop. Loop and surface, they are different, right? So this is basically this, not with this loop. Okay, so this is going to be the flux. So you will be given B, you will be given A, and this loop is going to act like an area, and you can integrate, find the phi. Now let's look at it. What EMF says. It says whatever the flux we are getting, this must be differentiated over time. So that means this flux must be a function of time. That means this flux must be changing. If this flux is not changing, that means if it is constant, then you'll find this answer will become 0, because we know for a constant differentiation is always 0. So there will be no EMF coming in. EMF will be coming in only if the flux is changing. So whatever this entire statement is, it has been covered in this particular relation, right? And once we got this EMF, as we have talked earlier, we can easily find out what the induced current is going to be. So let me write this. So induced current through the coil or loop is going to be I is equal to EMF upon R, where R is the resistance of that loop. And we can place the value of E, which is -1 upon R, and d phi B upon dt. This B is simply a subscript that indicates we are talking about the magnetic nature of flux. Fine, so these two formulas are coming because of the Faraday's law, and these two we need to remember, and we need to learn how to use these two formulas in order to get induced EMF or induced current. Point is, if you get this induced EMF, induced current can be easily identified just by dividing by R. Here R is the resistance of the loop. So R is resistance, that we need to keep in mind. So if the resistance is given to us, we can use this resistance in order to find out the induced current. So that's what the Faraday's law is. Now we will be trying to apply this law. So let's consider this example. It says a uniform and constant. So it's a uniform and constant magnetic field that has been applied. As shown in these two figures, we need to find the magnetic flux, and we need to find induced EMF in these two conducting loops, or the two cases that have been shown to us. So we can think of about them. So first thing that we need to find is the flux. So how to get the flux? Flux is integration B dot dA. And we have talked about that if it is uniform, then it can be written as B A cos theta. B into A into cos theta. And then how to get this EMF? EMF is minus d phi by dt using the Faraday's law, right? Now let's talk about the first case. So if we are talking about this first case, so how much the flux is going to be for this case? So area, this is the conducting loop, and this is a B. So loop area is going to be perpendicular to this. maybe inside, maybe outside, so whatever. Let's consider it outside. So whenever there is a plane surface, area can be considered perpendicularly in either of the two directions, and if it is curved or closed, then outward direction we consider. So this is area vector and this is B vector. So there is an angle 90 degree coming in. So you will write it as a B into A into cos 90 degree. And we know this cos 90 degree is 0, so you'll find the flux through the first is going to be 0. Since flux is 0 and 0 is a constant, so EMF is also going to be 0 because we need to do this minus d upon dt into 0, and 0 differentiation is a 0. So that means in this first case, neither there will be any flux passing through, nor there will be EMF, because the flux is, if there's no flux, then there is no change. If there's no change, EMF is 0. Similarly, we can talk about the second case as well. In the second case, we need to find this flux, so we need to say that B into A into cos theta. Can we identify theta? B is inside, we can also consider A is inside or outside, choice is yours. Generally, we consider in the direction of B. If we are writing simply magnitude, so it's going to be 0. So we can say it's going to be B into A, and A is given as pi r square because that's a circular loop, closed loop, and the r is given as a radius. So that becomes the flux. Now you see this B is a constant, that's not changing, r is not changing, hence phi is a constant, so this came out to be constant. And if it is a constant, then it will have no induced EMF, because for induced EMF, flux has to vary. So if we write mathematically, this is going to be minus d upon dt of this term phi, and this phi is a constant. So since this is a constant, it becomes 0, that means no EMF. So in this case, you'll find flux will be passing through the loop, but flux is not changing, hence no EMF is coming. Hence you will say no current will be running on this, neither any current will be running in this. Okay. So that's a basic example that relates flux and change in flux in these two cases. Okay, after theoretically understanding this Faraday's law, we need to learn what this Lenz law is. And this Lenz law, along with this Faraday's law, will complete this induction aspect, at least the base part of it. And this Lenz law is also basically hidden in the Faraday's law somewhere. When we write this EMF, we write this EMF as minus d phi by dt. So this minus sign was trying to say that EMF opposes change in flux, and that's what the Lenz law is. So Lenz law basically describes this Faraday's this direction aspect, or the aspect of induced EMF and induced current. So if I write the statement in short, it's going to be like this: induced EMF and induced current So whenever the flux changes, they come in. Induced EMF and induced current are such that basically it's trying to explain the direction of the current and the induced EMF. They are such that they oppose the change in flux. They oppose the change in flux that created them, that creates them, or created them, that created them. So whatever the flux change creates induced EMF or induced current, so current and EMF will be in such a way so that they will oppose. What they will oppose? Change in flux. So this is together, that has to be read together. Change in flux. So induced EMF and induced current does not oppose the flux, rather they oppose the change in flux. So first we need to see what is the change in flux, then we need to oppose them, and then we need to identify which current can oppose this and which type of induced EMF can oppose this. Now change in flux will be of two types. Either flux will be increasing. So if the flux is increasing, then induced current will try to bring down that flux. That means induced current will be in such a way that this current will produce its own magnetic field, and that magnetic field will try to reduce the flux that was increasing. So another flux will be coming in and the current will try to reduce that flux. And similarly, if the flux is decreasing, then this decreasing has to be opposed. To oppose this, the current will be running in such a way so that it will have its own magnetic field in such a direction that its flux supports this flux. That means the decreasing flux which was decreasing, that is try to increase that flux. So since this flux is decreasing, so opposing this decreasing means you try to increase this flux, right? Here you try to decrease the flux because the flux is increasing. That's how the oppose goes in, right? And this has to be understood, and for that sake this example can be helpful. And in this example there are four cases have been illustrated over here. This is a conducting closed loop, so that's a loop, and this is a bar magnet. So we have a bar magnet and a loop. Now loop is having no current, and bar magnet is there. Now when there's a bar magnet placed, let's say this is south part, this is north part, we are talking about this first part, so we will see the field lines will be running like this as shown by these lines, and some of the field lines will passing through this loop. And if you keep this bar magnet fixed, that means not moving, stationary, and keep this stationary, then the number of field lines that will be crossing this loop will be constant. So flux will remain constant, no current will be passing through. But if you start moving, let's say bar magnet as shown over here, if we start moving it downside, so you'll find as it goes downside, so more number of field lines will be crossing this. Why? Because some of the field lines were going like this. And as this comes downside, so these field lines will start passing through the loop itself. So that means the flux will increase. So in this particular case, or the first case, you'll find the flux is increasing. The flux is increasing. Now this loop has to get some current. This loop has to get some current. Now what type of currents it can get? It can get the current the way as shown over here, let's say in this way, or maybe in this way, because current can move on a loop in either of the two ways. But out of the two ways, which way has to be considered? That's what the Lenz law says. Lenz law says that out of the two, you consider the one which opposes this cause. So this was the cause, and now this cause has to be opposed. So that means current should come in the way so that the flux started decreasing. And if you consider this current that has been shown over here, then you'll find because of this current, magnetic field lines will be creating in the upward direction, because whenever there's a current in any loop, then there's a magnetic field. This magnetic field that I'm drawing with this red color is coming because of this current that has been induced. And how this will be upside, use the right hand rule. As per the right hand rule, this will be the magnetic field is coming in. Now this magnetic field will cause some flux to pass through the loop itself, and this flux will be in the direction upward, whereas the earlier flux was coming downward direction, and it was increasing in the downward direction. To oppose it, if the flux comes upward direction, so its increasing nature will be opposed. Hence we will have the current in the direction as shown in this particular arrow, this way. Now why not in other way? If you consider this, then it will become crystal clear. Suppose I have considered in this way, then this flux will come out to be this. This will be flux due to the induced current. So we can call this as induced flux. And this induced flux will be in the same direction where the original flux was there, and which was increasing. So this will be added up and it will further increase. But we don't want it to further increase, rather we want it to oppose. Hence this direction of current is not acceptable, and the direction that we taught earlier, that means this direction is acceptable. Alright. Now similarly, can you identify why this direction of current will be coming in this case? So if you try to understand, then you'll find this time this bar magnet is being moved upside. So since you are moving it upside, then you will say the flux is still downside, because the field lines, flux is in the direction of field lines, so field lines will be going through. So this is the flux. And what will be cause for this induction? Whether increasing flux or decreasing flux. When it goes upside, so you will know some of the field lines will start crossing outside. So that means over the time the flux will reduce. So cause is flux is reducing. Now this flux reduction has to be opposed. So current will be coming in this way, so that reduction in flux is opposed. And we haven't talked about earlier, if the current is in this way, then the magnetic field will be coming towards downside and flux will be downside. So you will find the flux will be added up. So flux will be added up, that means it opposes the decreasing of the flux, right? So in this case, you'll find the induced flux should come in the direction of the original flux, so that it opposes the reduction in flux. So in nutshell, we can say if the flux is increasing, then the induced flux must be opposite to it, and if the flux is decreasing, then the induced flux must be in the direction of flux. So this is the crux of the Lenz law. Similarly, there are two more pictures you can think about and see whether the directions are correct. In this case, the south-north have been reversed. So if this is the south, so flux will be passing now upward direction. So flux is in the upward direction. And if you take this bar magnetic downside, so you'll find the more flux will be coming in. So that means here the flux is increasing. So increasing flux is the reason. And that means induced flux come opposite to this. That means induced flux must decrease it. And if you consider this sense of the direction of current, so magnetic flux will come out downside. So this is flux induced. Now you say this induced flux is opposite to the original flux, which was in the upward direction. Hence it will be subtracted. Hence it will decrease it. Hence this direction of the current is correct. Similarly, in this case, if the bar magnet is moving upside, then you'll find this original flux, that is this flux is going to decrease. So this flux is going to decrease. Since it is decreasing, so current must support this. So current will be running like this, so that it gets its own flux in this direction. That's induced. And this decrease will be opposed by this, so that you will find the Lenz law is valid. And here the cause of flux was decreasing. Cause of this induction was decreasing flux. Hence the induced flux came in the direction of original flux. It might seem a bit complex, but if you go it by twice and thrice, you will find what I'm trying to say. Simple term is, first find what is the change in flux is, then oppose that. How you can oppose it? If flux is increasing, then we can conclude over here. Then what we need to do? Then the induced flux should be opposite to flux. This should be opposite. Should be opposite in direction to phi. And if the flux is decreasing, then induced flux should be same direction, should be in same direction as phi. So in terms of flux, you can remember that going to be easier. If the flux is increasing, then find the current in such a way so that the induced flux comes opposite to the flux direction. And if the flux is decreasing, then find the current in such a way so that the induced flux comes in the same direction as this flux. So there are two terms that have been mentioned. It has to be opposite direction when it is increasing. It has to be same direction when its flux is decreasing. And this is how the change in flux can be opposed. Okay. And once this is clear, we can take one example to make it more clear and see how it can be applied. So let's see this example. It says find the direction of induced current. So we need to find the direction of induced current. And this coil is shown to us, and magnetic field is inside, and it is increasing with time. So we need to identify the current directions. That means we need to use this Lenz law. So magnetic field is into the plane, so that's a perpendicular to the plane, and this field is increasing. Field is increasing. So what the flux is going to be? So how we are going to think and how we are going to use that law? First we will look at the flux. Flux is going to be, B is a uniform, we can think of it. So that's a B into A into cos 0. That's a B into A. So that's a flux. And this flux is into the place. So that flux is into the board. So because the flux direction is the direction of the magnetic field. And this flux will be increasing because B is increasing. Area remains constant. So we will say the flux is changing, and this flux is basically increasing flux. So flux is now increasing. Current has to come on this loop. There are two options. Either it can be in this way or it can be in this way. So we can think of both of them cases, or we can think of what we need to find or in what direction it should be. So what the criteria is. Criteria is this increasing flux has to be decreased. So that means what we are going to now find it out, that the induced flux, so that means flux due to induced current, should be opposite to this. So since this is into, so this must be this, this should be outwards. Should be outwards. Why we are targeting this as outwards? Because this flux which is increasing is inwards, and to oppose this increasing flux, we have understood the rule. If the flux is increasing, then induced flux should be opposite to that, and opposite will be outwards. Making sense? So this is going to be outwards, and now if you want flux to be outwards, that means you want the magnetic field to be outwards. So magnetic, if you want to run a current on this loop in such a way so that the magnetic field comes outwards, so what should be the direction? So we can use the right hand rule. So if we choose this direction, let's say this is the direction if we are choosing, so you'll find using the right hand rule and curling this or right hand fingers, the thumb will be outwards, so you'll find it's going to be in the outward direction. Makes sense? And if we are choosing this current, so you'll find this will give the magnetic field into the plane. So our purpose is to get the magnetic field outwards, because flux has to be outwards. So this direction is going to be direction of current. So you can show that this is going to be the direction in this conducting loop. So in the coil, the current will be moving in this anti-clockwise sense. Making sense? Now, and another case could have been if there would have been a word called decrease. So in case it is decreasing, then we will say that this is decreasing, then decreasing flux has to be opposed, and then as per the rule, induced flux should be outwards, so that it opposes the decreasing nature, hence the current direction will reverse. Okay, so what do you need to do? First find the flux, find its direction, check how the changing is taking place, and if it is increasing, induced flux has to be opposite to it. If it is decreasing, induced flux has to be in the direction of flux. Okay. So this is about Lenz law and Faraday's law. Very important theoretical lecture, and you make your notes and all that. And if there is an issue, let me know. And in the upcoming video, we will be having a couple of questions based on this, because in examination you can expect one or two questions based on this EMI, directly or indirectly. Right. So this is all for this video. Thank you for watching.